Yes, as always, I think feel free to interrupt and ask questions while the talk's ongoing. So anyway, I'll let him take it away now.
Okay. Thanks a lot for the invitation and for being here today. I know it's the end of the semester. At least it's the end of the semester for us. I assume it's also for you. So yeah, today I want to tell you about a topic I've been kind of obsessed with for the past couple of years, which has to do with measurement-induced phase transitions. So it's been a relatively active topic, and you might have heard about this elsewhere, right? So I'll try to give you kind of a general overview of what the field is about, why people are excited, what's new here. So about half of my talk will be some kind of more, if you want, introduction to the field, where I'll summarize at least how I understand those transitions. And the other half of my talk will be about some really more recent topic, which has to do with something we call charge-sharpening transitions, which will come from the interplay of quantum measurements and charge dynamics. Okay, and yes, please do feel free to interrupt if you have any question at any point. Okay, so let me just start by acknowledging my collaborators. I've actually been working on this with many people. I'm not going to list everyone, but in particular, let me just emphasize the junior people on this. So my student Utkarsh, who's graduating now and moving to KITP, and my current postdoc on this, Fergus Bad. And let me also thank Drew Potter in particular for some slides. Okay. All right, so let me just give you kind of a general introduction or where I'm coming from on this. So this talk will be purely about quantum dynamics. Okay, so as many of you know, like condensed matter physics has kind of evolved over the years, and we used to maybe think of setups where we had systems that were in thermal equilibrium and we're interested in ground state properties and low energy physics and different phases. And of course, we still do, but there's another completely different mindset when it comes to thinking about non-equilibrium quantum systems, which is motivated by the advent of many different experimental platforms. And the type of questions that you start asking about many-body quantum systems in this setup are very different. If you imagine that you just have your system, you can control it and engineer it pretty well, you know the interactions, and you can prepare well-defined initial states and let the system evolve in isolation or not, depending on your setup. And there are many fundamental questions that many people in the audience and myself have been thinking about related to thermalization, whether you reach interesting non-equilibrium steady states, whether there's any notion of universality, which is one question that I like particularly, right? In dynamics, is dynamics completely messy because it's a high energy process, or do you have universal phenomena that can emerge? Okay. And in particular, it's really an interplay of unitary quantum dynamics, some maybe coupling to some environment, and physics of having an observer. Okay. And then so in this talk, the distinction between having an observer and having an environment will be quite important. Okay, I'll come to this. So there won't be any Hamiltonian in this talk. Actually, there will be in the end, but there will be kind of effective Hamiltonians. But like, so the type of quantum system I'm going to be thinking about are quantum circuits. Okay, and so this is proven to be a kind of popular setup in recent years. So this is some figure from the Google experiment, and I'm sure many of you have seen. And so I'll be thinking of quantum circuits. And so in case you're not too familiar with this, let me spend a few minutes just explaining really how it's defined. So I'll be thinking of one-dimensional systems. Some of the things I'm going to tell you about really generalize to higher dimensions, but for simplicity, let's imagine a 1D system. So, and I'll imagine I have a discrete lattice with a bunch of spins. I'll call them qubits or qubits. They could have d levels, but let's say qubits for now, 2-level systems. And instead of considering some Hamiltonian evolution, I'll think of just unitary dynamics, which is generated by this following circuit. Okay, so you have time going upwards where you just add layers of gates. So each red rectangle here is a unitary gate that act on nearest neighbor qubits. And I'll take those gates to be, so you can imagine this is coming from trajectorizing some Hamiltonian evolution. But here I'll imagine those gates are very far from identity and we'll actually take them to be random in space and in time. And so we think of this as a toy model for quantum dynamics. And so this is going back to works by Adam Nahum and collaborators. And the nice thing about this is you can get a handle analytically on many quantities like entanglement, operator spreading, how hydrodynamics is emerging, and so on. Okay, so there's no conservation law yet. I will put back conservation laws later. So there's no energy, no Hamiltonian. So the only ingredients that you keep, I'd say really in the spirit of random matrix theory in my mind, you keep just unitarity, so it's quantum dynamics, and you keep locality. Okay, so locality is because you have this brick wall pattern and like the gates only act on nearest neighbor spins. So you have an obvious 1D geometry here. So you imagine you start your system in say a pure state, say a product state on say a computational basis. Even though your full system remains in a pure state at all times because time evolution is unitary, if you look at local observables in the subregion A, we know that the reduced density matrix that will describe those observables will become quickly mixed. Okay, so this is the process of thermalization. You will forget about your initial conditions and about all the properties of your initial state will become encoded in highly non-local degrees of freedom. So if you only focus on local conserved quantities, on local observables, in that circuit, since there's no conserved quantity, really what happens is that your reduced density matrix on one spin or on a few spins will just approach a completely mixed identity reduced density matrix. Okay. So if you compute the von Neumann entropy of that distribution of that reduced density matrix, which is called the entanglement entropy, it just goes linearly with time, and it saturates something extensive with the size of the system. Okay, so that's a process of thermalization. In the context, it's believed to hold, in general from any many-body quantum system, really, at least generic enough. And here for quantum circuits, you can just show this analytically. Okay. So far, there's nothing super exotic. It's just a process of, if you want, thermalization, but there's no conserved quantity, so you thermalize to infinite temperature. So those circuits, basically, since they're random, nothing is conserved. If you look at observables, they kind of have a featureless behavior. So now let's add another ingredient, and this is this concept of measurement-induced transitions. Okay, so this was introduced in those two very nice papers by Brian Skinner, Romain, and Nahum, Lee, Chen, and Fisher. They appeared at the same time. And their idea was to add some competition between unitary dynamics and another ingredient in quantum mechanics, which is just observing the system. Okay, and I'll precise what I mean and why it's important in the next slide. But for now, just think that those are measurements as the ones you learn, and when you learn quantum mechanics, you do projective measurements. So now what happens is you have still the same circuit. I just changed the color of my gates. So this is space, this is time. And at each time step, you have those blue dots, and those blue dots with some probability P, which is some parameter in the problem, you will measure the states of that qubit. Okay, and so you measure as in quantum mechanics. So the probability of the measurement will depend on your wave function. This is you have Born probabilities. And once you measure, if you find that your spin is up, so you measure in the computational basis, you will find your spin is up or down, you'll project your wave function. Okay. And you do this with probability P. And so the basic idea of why this gives you an interesting, there's only two ingredients here. There's chaotic or scrambling dynamics, if you want, from unitary dynamics, and measurements, and that's it. And so it seems very general, right? So it's a very featureless model in some way. And the claim is that this leads to a very universal type of phase transition, which were discovered in those papers numerically, right? So the idea is that if P is 0, it's just unitary dynamics random circuit. Entanglement grows very fast. Okay, so for now, I'm going to talk mostly about entanglement, but I'll switch observables halfway, like in a few slides. Okay, so if you don't like entanglement, it's okay. I'll switch eventually. But so for now, let me focus on entanglement. So like the von Neumann entropy of that reduced density matrix. So if P is 0, again, entanglement grows very fast. And this is what you see on that plot in the lower left corner. If P is 0, entanglement is increasing. So this is entanglement in a steady state. So you run those circuits with, for a long time, and this is plotted versus the size of the subsystem that you consider. So this is plotted in log-log plot for some reason, but this is a linear slope. Okay. But as you crank up the rate of measurements, this entanglement will lower. And the idea that the way you can understand this is, of course, if you take P as 1, it means that every single blue site, you will actually measure the state of your qubit. So first site, you'll find your qubit is up. Second site, maybe you'll find it's down. And you do this on every site. And of course, when you do this, you just project. So at the end of the day, what you have is a product state, which is just a classical state with no entanglement. So in some way, like the measurements are disentangling your system, right? You just project them back onto. So if you have enough of them, what those authors claimed, mostly numerically, was that if you tune P as a function of P, if you crank up P enough, there's a transition where the entanglement will eventually just saturate. It will not scale with the size of the subsystem anymore, so which is known as area law scaling versus volume law scaling. Okay. So that's the basic idea of what those transitions are. And again, I'm formulating them in terms of entanglement, but entanglement is not really crucial here. Okay. So again, please do interrupt me if anything is unclear about the setup, because I'm going to be using this basically throughout the talk. Okay. All right, so there's one important maybe conceptual point that I should really emphasize here. So this transition, it's very interesting because it's very fundamental, and you could think it basically occurs everywhere around us all the time. But on the other hand, is actually very weird, and it's pretty hard to observe. So let me explain that. And to some extent, there's you can debate whether you want to think of those transitions as very physical, either extremely physical or kind of weird, depending on your perspective. Okay. And so for this, you can think I'm dealing now with open quantum systems, right? I don't have only unitary dynamics. When I measure the system, I do something different. And so when you learn about measurements, it might have been that you saw two different perspectives. So one perspective is that of quantum trajectories. It's where you imagine that, again, you have a system and you have your observer. And when you measure, again, you have a wave function. And after measurement, what you get is a new wave function, which is projected on the measurement outcomes. And again, this occurs with a Born probability, which here I haven't normalized my wave function. So it's just the norm of that wave function. Okay. And then you do another measurement, and you keep doing this. Okay. And so in this quantum trajectory picture, if you want, you have multiple universes where you have different outcomes of the measurement, and it gives you different wave functions. And your wave function always remains a pure state. Okay. But in many quantum mechanics books, you will also see a different perspective, which in more quantum information language would have the name of quantum channel, where you can imagine that you can trace out the observer, and you can think of it as an environment. And so your system is now in a mixed state, which is in a superposition of all those measurement outcomes, right? And usually, actually, those two perspectives are kind of argued to be equivalent. Okay, and in the context of this talk, they will actually be very different. So let me explain briefly why. So usually, when you think of typical observables, which I'm going to call linear quantity, and linear will be in the density matrix. If you want to take the average of the expectation value of some observables, say spin or whatever or something, and you want to average it over quantum trajectories, it would be something like this equation. So you sum over all possible measurement outcomes. Okay, your spins being up or down, they come with some probabilities that are called Born probabilities. And this is just the expectation value of O in that trajectory, okay, with now properly normalized. And if you do this, your PM is the norm here, so this cancels out. And so this is precisely the same as computing trace of rho O, where rho bar is like this average density matrix. Okay. So averaging over those quantum trajectories is the same thing as like dealing with that mixed density matrix. Okay. And in the context of everything that I'm going to tell you today, if you look at this average density matrix, nothing is going on. So if you average over the measurement outcomes, so if you forget about the fact that you actually have an observer, and that density matrix is completely mixed and nothing interesting is happening in it. However, if you think that quantum trajectories are what's physical, okay, and that you can compute different moments. So for example, you could take the square, okay, you could compute nonlinear quantities, like say average the, again, square of some observable. Okay, so you sum again over measurement outcomes over bound, you have this bound probability, but now you take the square of that expectation value. Okay, and here you can try to simplify it, and the bottom line is you cannot write it in terms of that average density matrix. So I'm making a big deal out of this because it's really crucial. So observables like those nonlinear ones are really the observables in which you can see that this measurement-induced phase transition I mentioned, and everything else that I'm going to tell you about is only visible in quantities like this. Okay. So I should mention this has important consequences. If you think of measuring an observable like this one on the right, you should be able to convince yourself that this doesn't sound so trivial, right? When I say measuring, I mean in an actual experiment. Okay, so something on the left is okay, but something on the right, even if you have a nice, quantum computer or quantum simulator, is actually pretty hard to do because you need to be able to prepare your system over and over again in a given wave function psi m with a given set of measurement outcomes. So at least very naively, if you wanted to measure this quantity on the right, you would need to post-select on the measurement outcomes. Okay, so that would be exponentially hard in the number of measurements that you do. Okay. So, okay, so that seems, this is an important caveat, and I'll come back to this. And of course, people have been thinking about ways to bypass this. Okay, and there are ways to actually improve the scaling, but I won't talk too much about this. Okay. So it's a very fundamental quantity. This transition is very fundamental. It's there in the trajectories, but it will only show up in quantities like this one, which explains why you just don't we don't see that transition all the time in any experiments where we just measure stuff. Okay. Okay. So let me just show some results, right, of those original papers. So this is just from the first paper. So this one is from Leach and Fisher. What people really are computing is just this Renyi entropy, right? So it's a variant of the von Neumann entropy. And this is nonlinear in the density matrix. So this connects to my previous slide, right? This is not something, if you average over measurement over trajectories, this quantity, this doesn't have a simple expression in terms of the average of the density matrix. Okay. So the entropy of that reduced density matrix has a phase transition, and people were able to do standard finite size scaling. There are a bunch of critical exponents. There's a correlation net exponent, which is near 1.3. There's a dynamical exponent relating space and time, which happens to be exactly 1, and I'll tell you why. And there's even some numerical evidence of conformal invariance, and I'll come back to this. Okay, which is fairly non-trivial. It's a highly dynamical problem. Again, there's no low energy physics here. There's no reason to have Lorentz invariance, between space and time. But yet all of this is happening near that phase transition. Okay. Maybe again, let me just take a brief pause just to see if there's any question. Okay, so maybe I'm only telling you things you already know, but okay. All right, just very briefly as well. So this would be the topic of another talk, but let me tell you, so far I mostly just showed you numerics. We understand analytically quite a few things about those transitions. And so the way we understand them, or at least the way I understand them, and I suppose people have different perspective, is you can actually understand many things analytically through exact mappings onto statistical mechanics models. So this is quite a common technique in the context of random quantum circuits. Here, so one complication is that, we want to compute things like that. So nonlinear in the density matrix, we want to average a log of some power of a density matrix. And averaging logs is complicated, and there's no really way around it here because of the measurements. And so what we did in those papers, and there was also a paper by Ehud Altman and collaborators that did this, is introduce some kind of replica trick, right? So whenever you want to average a log in physics, you can maybe say that you can average moments of a quantity, and then through this formula, which is exact, you can hope to reconstruct the average of the log, right? So of course, this has the usual caveats of the replica trick. So that is, we claim that it's not so hard to average over measurement outcomes and over random gates and things like this, quantities like this one, but then we want to analytically continue to Q being real instead of integer, to K being real, sorry, instead of being integer to take this limit.
Question.
So, yes, go ahead.
Just to make it clear.
Yeah.
So you have two kinds of randomness here, of course.
Yeah.
One is like the environmental one, that's the measurement. Okay. And as you explained, you want trajectories, you don't want the channel. That's clear.
Right. Yeah.
So what you're doing is trajectories given some set of some outcomes of the measurements.
That's right.
And then you also have the random circuits.
Correct.
Okay. And I think you can, then I guess you can average over the random circuits without making your pure state into mixed. Yeah.
Yeah. Yeah, that's right. And so using this replica trick, at the end of the day, we're going to average everything at once because the replica trick is basically mapping to something.
The safest thing is to average at the end.
Yeah.
Okay.
Yeah, that's right.
And you could stage your averaging, but the key thing is you don't average too early.
That's right.
Okay, fine.
Thanks. Yeah, no, that's correct. That is correct. Yeah. That's absolutely right. So here, like once we actually do this, once we use the replica trick, we are going to average over the circuits, meaning like the gates, the position of the measurements and the measurement outcomes. But indeed, there's one randomness that's special, which is like those measurement outcomes, and that you want to keep until the end, if at all possible. Okay. So thanks. Yeah, that's a very good question. So something I'm not going to show at all today is like you can actually map averages of like, you can actually do this average analytically. And again, that would be the topic of another talk. You can have a look at those papers if you're interested, but you can compute average of quantities, like you can average over circuits of a measurement outcomes exactly like powers of trace of a density matrix. And you can map this onto something that looks like a 2D classical stat-mech model, which is basically defined on some like hexagonal graph. Okay, so it's a very non-trivial mapping and it's not so important for what I'm going to say today. And somehow the degrees of freedom of the stat-mech model end up being permutations. And the permutations of those replicas, so I have a bunch of like copies of my system. I have Renyi, N is a Renyi index, so in K is some replica index, and I have a copy from the Born probability. So anyway, and you have permutations of those copies. Again, it's a completely irrelevant technical detail for now, and we know how to do this for hard gates, and you can take different subsets of gates. So something that people like are Clifford gates that you can simulate up to long times, and we can also formulate statistical mechanics models for those. So why is that useful? Well, we have a better handle, of course, on like 2D classical stat-mech models than we do on like the original problem of computing entanglement entropy in some quantum circuit with measurements. So now this is just a, genuine 2D classical stat-mech model. The only caveat is we need to take some replica trick. Okay. And so this gives you some very nice picture, and I think that's the picture is the only important point here of those transitions, and it becomes just like ordering transition in the stat-mech picture. So for simplicity, imagine the stat-mech model is just an Ising model. It's actually a bit more complicated than that. But so you imagine you have some Ising model, and as a function of P is basically like temperature. So when P is large, you'll have a paramagnet, and when P is small, you'll have a ferromagnet, a symmetry broken phase. Here, the symmetry is some replica symmetry, but again, it's not that important. And if you follow that mapping, what entanglement maps to is basically some line tension of what domain will at the boundary. So again, it's not especially intuitive, but it's now becoming relatively standard picture. It's called mountain brain picture or directed polymer picture. People have different names for it, or domain wall, but basically through all those mappings, like entanglement maps onto computing some domain wall tension in a stat-mech model. So what do I mean by domain wall? Imagine you take an Ising model and you have a boundary, and let's say all spins are up, you fix them. But in some region A, which your entanglement region, you force the spins to be down. Okay, and so you'll force, again, the domain wall, which is here in red. And of course, if you have a ferromagnet, the free energy cost for like of inserting this domain wall is extensive. You have some line tension if you want. And so this maps to entanglement, and this corresponds to volume law scaling of entanglement, whereas at high P, it corresponds to high temperature. Here, creating domain wall doesn't scale with the size of your interval because you have domain walls everywhere. It's a paramagnet. Okay, you have a domain wall condensate anyway. Okay, so again, I haven't shown this mapping, right? So you can have a look at those papers if you want the technical details, but it gives you an understanding of that transition, at least in fairly qualitative terms. And the nice thing is, of course, again, we know a lot about free energy cost of domain walls in StatMech models, right? Okay. And the final thing I'm going to say about just the general case before switching to the more recent stuff is that, okay, in general, the StatMech model is still complicated because of this replica trick. We have to take this replica limit. There's one limit in which everything becomes nice and analytically tractable, and maybe it's a simple and intuitive physics. If you take, instead of qubits, you imagine you have D-level systems and you take D very large. There, the statistical mechanics model really simplifies dramatically, and it's actually written the partition function here. It's just something defined on a square lattice, and that's the partition function. You just have a Kronecker delta interaction between those spins, which are permutations. And so this is a Potts model, and it's known how to analytically continue it when you take Q goes to 1, which is the replica limit that we want. And it maps onto a very simple problem, which is bound percolation. Okay. And of course, it should be relatively intuitive, maybe why percolation is related right here. Like if you measure enough, you imagine you can have like some percolating cluster of measurements and that it should play a role. And indeed, in that limit where you have very large on-site Hilbert space, the physics is basically just classical percolation. Okay. However, and we also know that like for what people actually observe numerically when you do qubits, this is not percolation. So that limit is special. If you want, there's a relevant perturbation that takes you away from percolation. So it's pretty similar to a quantum Hall plateau transition, if you want, or things like this. It's just like a quantum percolation problem. So there's a simple limit where you have a percolation limit, but in the actual transition that people care about, it's very much a non-trivial problem. Okay. Okay, so I'm done with my pretty extensive introduction to measurement-induced phase transition. So apologies to those of you who already knew a lot of that stuff, but okay, hopefully that wasn't too fast for those of you who didn't. And again, if you have questions, now would be a good time because I'm just going to switch gears and talk about really more recent stuff.
So what were, are there some general assumptions about the types of gates you consider here, or?
Yeah, thanks. Yeah, so now, I mean, in general, like okay, in the StatMech model, originally it was really important we had hard gates. Now we can basically do, I'm not going to say any family, but we have a pretty concrete recipe to average over different subgroups. So I had like some cryptic comment here. So the reason you have permutations is related to the so-called Schur-Weil duality in math. So you have unitary gates, and like the reason you have permutation is because of this math result. And formally, like the degrees of freedom of like the StatMech model, they become to the so-called commutants of whatever group you have. So anyway, there's a general math formalism if you want. We know how to construct the StatMech models quite generally. So we did it for Clifford gates, for Clifford group in that paper with Yadong Li, Matthew Fisher, and Andreas Ludwig. And I mean, the recipe we had there, we could generalize to different subgroups. So in principle, we could do different families of gates. And you get different universality classes. Okay, so I see there's a question in the chat. Is the percolation limit only valid for S0? Okay. Is there a classical model applied for higher order entropies? Very good, thanks. That's a good question. So, so indeed for S0, the Hartley entropy, there's always a percolation transition. And so this was pointed out in the first paper by Skinner and collaborators. That's probably what you're referring to. So here in the large D limits, where you take large on-site Hilbert space, every single Rényi entropy, including like the von Neumann entropy, become controlled by percolation. But you're right, like if you do qubits, S0 is special. But if you do like von Neumann entropy or second Rényi, then they will have non-percolation transitions. Very good, thanks. Okay. Okay, so let me say, now add a new ingredient. Okay, so we're starting to understand those transitions pretty well, and there are many interesting questions you can ask, in particular, like how, are they classical variants? Like, can you actually realize them in experiments? How you actually measure this? Are there like different ways to bypass this post-selection problem that I told you about, so on and so forth? Can we understand the transition? Like, what universality class do we have? So one direction we started taking recently was like, can we go back and add symmetries? So, there are many motivations for this. One is we have a phase transition, and you can say, okay, we know in equilibrium, having different symmetries will lead to different universality classes, right? But there are like really deeper reasons to do this. So if, in particular, I'm going to consider systems that have a U1 charge. Okay, so imagine like total SZ is conserved. Or imagine you have particle numbers, so the gates can kind of make particle hop, but you have a total conserved particle number. Okay. And our motivation was mostly, we know that if you have a U1 conserved quantity, again, that quantity is constrained to have some hydrodynamic behavior. You can show this in U1 circuits, they'll obey some diffusion equation, right? And we know like those hydrodynamic modes, if you want, they'll scramble in a different way than like the way the information about those modes is spreading in the system is very different than like quantum information, right? And so you can ask about the interplay of symmetry and entanglement growth. And so we're not the first ones to do this. People had done this without measurements before, in particular Kurt and collaborators. And it's already known that like having a conserved quantity really modifies the way entanglement is growing, for example, even without measurements. Like different Renis now, like higher Renis grow as square root t, for example, if you have a U1 conserved quantity, right? And physically, there's also some pretty nice question that you can ask, and that's actually the way we understand this transition now. The next transition I'm going to tell you about is how much information about charge can an observer extract from local measurements, okay? And so the setup, if you have a system, and again, it has some quantum chaotic dynamics, but it has some conserved quantity, and again, you have maybe particles hopping and total number of charges conserved. And let's say you have, your state is in a given, your system is in a given charge sector. And let's say as an observer, you just measure the system, but you only allow those local measurements. And you measure, and maybe you see a particle here, but you don't see a particle there. And the question is, can you reconstruct the charge from those local measurements? Okay. And so it turns out there's a phase transition as a function of P. Okay, so of course, if you measure a lot, you have a lot of information. So you expect maybe you'll be able to reconstruct the charge. And if you don't measure enough, the charge remains hidden. And so actually, our current perspective on the stuff I'm going to tell you about today is really in that language, which sounds maybe more physical than like those post-selection schemes I was telling you about. Okay. So, but let me go back to circuits. So the way we're going to do this is, again, I'm going to think of, again, a circuit. I will imagine that on site now, I will have a qubit degree of freedom that I'm going to call the charge qubit, which again corresponds to that conserved quantity that I have. And I will actually couple it, and that's mostly for technical reasons, to a neutral qubit, so a D-level system. So capital D here is D squared. And the gates are basically just, they have a block diagonal structure just to preserve the charge of the charge qubit. Okay, but otherwise they completely generate random interactions, but they preserve this charge. Or again, think of this as a particle hopping or not, right? And the measurements, we basically measure everything at once. You measure the qubit and you also measure the charge qubits. We can separate those but it's not needed. Okay, so for simplicity, I'll just measure everything. Okay. So it's basically the same as before, I just have a bit more degrees of freedom, but on top of it, I have this charge that's moving around. And if you look at just the expectation value of what the charge is doing, it would obey some diffusion equation, right? There's some hydrodynamic behavior you expect at long times. So here's the claim. So there's another transition here. So just to show that there's really more than just this transition, this concept of measurement-induced phase transition is pretty rich, and there's actually a whole type of phase diagrams that you can get. So what I'm going to argue is that on top of like the phase transition I was already telling you about that I call PC, which separates something in entanglement between area law and volume law. Okay, there are different observables, but I'm going to call this the entanglement transition. There's actually a phase transition inside the volume law phase here. Okay, and so if you're used to like quantum dynamics, this might be a bit surprising, right? So usually we don't think of volume law states as like states where you can have interesting things going on. And here inside that volume law phase, where the state is highly entangled and highly scrambled, if you want, there's another phase transition which has to do with charge. And so I'm going to call this P sharp. In the different phases, I'm going to call charge fuzzy and charge sharp. Okay. And so formally, like there are two ways, I'm going to present at least two ways to think about this phase transition. There are really different ways. So one physical way will be that it will have to do with how long it takes to collapse charge superpositions. So you can imagine your initial state is a superposition of different charge sector, right? So maybe you have a charge sector where you have L over 2 particles. Maybe you have a charge sector where you have L over 2 plus 1 particles. And your quantum state is a superposition of those different charge sectors. And when you make measurements, the measurements, if you measure the system enough, you'll collapse the states of the charge. Okay, so that's maybe fairly intuitive. But the question is how fast? And there's a phase transition here, like before that phase transition, it takes a time that scales with L to collapse this charge. And so this L is something that can actually be understood from central limiting type theory arguments, so it's not too complicated. Whereas here it scales logarithmically. Okay, so here the charge superpositions collapse pretty fast. Whereas here they take at least the time that scales, linearly in L. Another way to think about this is you can look at just correlation functions. Just look at charge-charge correlation function, equal time. Okay, so this looks like a natural object, and you average this over trajectories. Again, you should consider that this is actually non-trivial because of the second term. The second term is the one that's non-trivial here, the disconnected part. That's the one that's non-linear. Okay, and the claim is that this has a phase transition where like it's algebraic on one side, whereas those charge correlations decay exponentially on the other side. Okay, and actually there's some. Okay, what I'm going to show is there's some Luttinger-liquid-like behavior in this regime, which again should be very surprising to you. It's not. There's no low energy physics here. So highly entangled states. Very high temperature, more at infinite temperature, and we get basically low energy type Luttinger-liquid behavior. So let me explain how we understand this.
Is always 2 or? Yes,
the exponent here is always 2. That's right. So that would be like charge-charge correlations in a Luttinger-liquid. Right. So if you measure charge-charge correlations, say in an XXZ chain in 1D in the gapless phase, you would find the same. We also know how to get continuously varying exponents. I'll get to this. They are continuously varying exponents here.
And so to distinguish these two, your initial state had to be like a mixture of U1 sectors?
No, so yeah, so like those equations, like for the correlators, there are long times where you collapse the charge anyway. So it doesn't matter, the initial state doesn't matter for like the equation that I wrote. So you can think of the transition either as like the dynamics of how you collapse superpositions, or if you go to some steady state, you have the behavior that I wrote here.
Okay.
And I'll show how we understand this essentially analytically. Okay.
Question.
Yes. Yeah.
So the two transitions are continuous.
That's right.
The P sharp and the PC.
That's right.
And then, if one thinks in terms of trajectories of measurements, this is a statement about a typical set of outcomes. In the sense, you will average at the end. You will average.
Mm-hmm.
In a large enough system that I'm saying, well, if I have a trajectory with typical set of outcomes,
that's right. It is typical.
Depending on P large or small, I get these phases.
That's right. Actually, the way we do the simulations is we sample trajectories with their own bound probability. So we're not sampling anything atypical. We're really sampling like typical quantum trajectories, and you see this.
Okay, thanks.
That's right. Yeah. So yeah, it's not about rare trajectories. It's really about typical behavior. So again, the way we understand this is through some stat-mech model. So let me briefly sketch, and again, I'll try not to be technical and just give you the outline. So we're working in this volume law regime. In this volume law regime, the stuff I was telling you, the other stat-mech model I told you about that had permutation degrees of freedom, it's in a ferromagnet. So those spins, if you want, they ordered. And if you try to write some effective Hamiltonian, it's gapped. And if essentially what you can do is integrate out, this will play no role. However, the charge degree of freedom will still remain. And we want some effective action, if you want, or some effective dynamics for what this charge is doing. So we can do this analytically, again, using some replica trick and so on. But the end result is so simple that I don't need any technical detail. What we find is that at the end of the day, like the charge is just obeying some very simple rule, which you could probably guess if, and charge is basically just diffusing, right? So it obeys a 6-vertex model, or more simply a symmetric exclusion process. So just a Markov process where, you know, I put some vertices here, but basically what happens is you have like time running upwards. If you have a charge coming in at a gate that has a 50-50 probability of just coming either on the right or on the left, right? Just because you have random gates, there's no bias here. So you just have 50-50 probability to do anything. Okay, and so if you have 2 charges coming in, you have 2 charges coming out by conservation, and you have 0 charges coming in, you have, of course, 0 charges coming out. So we end up with a completely classical model with those weights, which again only describe the symmetric exclusion process. And what do the measurements do here? Well, they basically act as quench disorder because they constrain. If you measure and you find a charge, like on that symmetric exclusion process, you constrain that you want to have a particle there. Okay. And so this stat-mech model that we have is basically just this disordered symmetric exclusion process or 6-vertex model where you have, again, a bunch of charges diffusing around, and you have a bunch of measurements that tell you whether or not you should have a particle on a given site. Okay. And once you fix the measurement outcomes, you say you had a particle here, particle there, 0 particle there, you basically want to count how many trajectories of charge were compatible with that, with those measurement outcomes. Okay. And you can easily convince yourself like that, you know, if you have too many measurements, that could be very constraining for what the random walks have to do. Okay. And the claim is there's a phase transition in that model. And Born probability here, you know, plays the role of Boltzmann weights. It's basically some anthropic factor of how many trajectories of charge are compatible with a set of measurement outcomes. So we can do actual numerics on the qubit model, or we can do numerics on like the stat-mech model. This is actually numerics on the stat-mech model. We can actually go to very big systems, much bigger than this, but like, okay, this is an old plot. But it does illustrate the purpose. You can, what is plotted here is the charge variance. Okay, so we're starting from a superposition of many sectors, and we average over trajectories of like that variance after a given time for different L's. And what you see is that there's a type of crossing. And so this crossing is real, and I will, okay, it's maybe not super convincing from this figure, but it's an actual transition. Okay. So how are we so confident about this? Well, we can actually understand this model mostly analytically using now relatively standard tools. So the nice thing is, because it's a statistical mechanics model, it's classical. So we can use the fact that it's non-unitary, right? Tells you there's some effective Hamiltonian that governs its dynamics. So at long times, it's like imaginary time evolution. And so the symmetric exclusion process corresponds to the Heisenberg ferromagnet. So this is a well-known result. Of course, it's not, we're not the first ones to notice this. Okay, so there's this relation between the symmetric exclusion process and this Hamiltonian. But here we only care about low energy properties, right? So long time dynamics will map onto low energy properties of this Hamiltonian. So this Hamiltonian has nothing to do, quantum Hamiltonian has nothing to do with the original quantum problem we wanted to solve. You know, we had quantum system mapping onto a stat-mech model, and now we do quantum to classical mapping, and we get some effective quantum dynamics. Okay, so at low energy, this is a ferromagnet, has magnons equals 2, and that corresponds to this charge diffusion. Okay. But now again, I mentioned that you have those measurements, and they correspond to some kind of disorder. And again, we do some replica trick, and we can write down some Hamiltonian that corresponds to this measurement randomness, and it's written here. So because we took some continuous time version, right? So I don't have discrete time steps now because I have a Hamiltonian. We also have to do a weak measurement version, and so this is the strength gamma. But you can think of gamma as p basically. Okay. And so what the measurements do, they force different replicas to agree.
Question.
So this is what, yes. Okay.
So we are thinking of this HU and then the HM as the generator of dynamics like this.
Correct.
Thanks.
Correct. Yeah, that's absolutely correct. So I'm still going in a time direction. Now it's imaginary time in my stat mech model. And so I have this part which describes the symmetric exclusion process, and this part which gives you the measurement. And so now this is a low energy, this is a Hamiltonian problem, so we can do a lot of things, right? And so in particular, we can do a spin wave expansion if you want, or we can write like a spin coherent state path integral. We can do standard field theory things. Again, there's nothing particularly exotic here. The only thing is, again, we have replicated our system. And what we find at the end of the day of this analysis of just taking this Hamiltonian, linearizing about some order states, so if you want, it's a Goldstone action. We find that at least in 1 plus 1D, and higher D things are more complicated, but if you have a 1D system, the dynamics kind of separates into two parts. We have a part that is, so the bars here are average over replicas. So we have a bunch of copies of our system. A runs from 1 to Q. Q is number of replicas. And we want to take Q goes to 1 at the end of the day. And so here, like the average bar means replica average. So those are things that will control the row bar, right? I'm actually using the same notation. So that's the property of the channel average over, averaging over measurements. And so this, okay, this looks, okay, if you're not, I don't know if it's obvious to you or not, but this action, it's just the action of a ferromagnet. So there's nothing exotic here. There's just the Heisenberg ferromagnet. It basically just describes diffusion. Okay, so what this action describes is just charges diffusing if you measure charge-charge correlations. The non-trivial part is actually the other one. So this describes, so pi is defined by this. It's basically a projector onto something that's not symmetric between replicas. And it ends up giving you Q minus 1 things that look like a Luttinger liquid or an XY model more precisely. Okay. And there's some effective superfluid stiffness, if you want, or stiffness that's given by square root of the strength of the unitary dynamics divided by the strength of the measurement. And so this sets what the stiffness is for this XY model. Okay. So, and there are like irrelevant perturbations and so on. So it's a well-defined field theory. We can do usual dualities and so on. Everything is under control, basically, right? So there's no really approximation, I would say. We're only making standard field theory arguments. And what we get at the end of the day is some kind of KT transition. Okay, for this model, it's just an XY model will have a KT transition. There are some minor subtleties with the fact that we're doing things at a boundary, that we have replicas. But ignoring this, our prediction is that you get some KT-like behavior, Kostelis-Thales-like behavior. Okay, you'll have vortices if you want in those fields, and they'll drive a transition, as in the usual Kostelis-Thales or XY model. And so we make a bunch of non-trivial predictions that we can check numerically. So it's just still checked in the StatMech model. It's hard to actually check this in ab initio numerics. So we can do StatMech, we can simulate the StatMech model to pretty-bit systems using tensor network techniques. Okay, so this is efficient because the original model is highly entangled. You have volume law entanglement. You would have no chance of doing TBD or any matrix product state-based algorithm, but the StatMech model is has low entanglement. So it's easy, quote unquote, to do, even with disorder. And yeah, and here are some results, and that will be basically, I'll end my talk with this. So you can look at charge-charge fluctuation. So here I'm using, again, spins, but you can think of it as a particle number correlation or SZ-SZ correlation. And for different measurement rates, and so this is plotted in log-log, what we predict from the field theory is, again, this would go as 1 over x squared. And below this KT transition, but above the KT transition, it should decay exponentially. And you can extract, you just fit Paolo's, this is the green line here. This is just naive fit of the exponent. You see it's basically stuck at 2, right? So this is just purely naive fits. And then at some point it starts deviating, okay? And this some point is actually where the transition happens. Okay, of course, we cannot really distinguish between exponential and some Paolo that decays with a very strong exponent. But we can go beyond this. We can also construct quantities that have continuously varying exponents. And so for this is really a non-trivial prediction of the field theory, if you want. So if we can construct string-like operators or vortex correlators, so we can construct operators that look like this. They're well-defined, right, on the lattice. This is actually just parity of charge. It's like product of z on an interval. So this is a non-local observable. So it's like a string order parameter, if you want. And if you compute, again, the average of the square of this of the trajectories, we predict that it has continuously varying exponents in that phase. And indeed, if you do the numerics, you see that very clearly you have continuously varying exponents. And from this, you can extract what we call the superfluid stiffness. Okay. And we can actually compute the superfluid stiffness in different ways. So the theory also predicts that, say, the variance of charge is logarithmic in that fuzzy phase. So because 1 over x squared, if you integrate it twice, you get a log. So if you look at the variance of charge in some interval, it's like in the Luttinger liquid, it has a log. And the prefactor also tells you about rho s. So, and here what you see in this plot is like extracting rho s from those 2 different methods. And, you know, they agree very, very well, I would say, right? Like, so keeping in mind, we still have relatively modest system sizes. We only go to 60 or something because of the disorder, but, you know, we can, I would say there's no really doubt that the theory is working very well here, at least for that StatMech model. So let me skip my next couple of slides and just jump to the conclusions, just so we can have questions. So, okay, I've presented a new type of measurement-induced phase transitions. Well, maybe not so new anymore, right? So originally people thought of them as entanglement transition, like they're very closely related to entanglement, but they really show up in different quantities. So in particular, I think the charge-sharpening transition that I sketched in the end, right? So it has to do with, again, the ability of measurements to reveal a conserved charge. In some way, it's a lot more natural and maybe simpler. You don't have to think of entanglement. You just have to think of measuring charge, right? That's it. That's all you do. And I didn't talk too much about this perspective. I focused on this StatMech model in universality class, but really now the way we think about this is like, if you wanted, again, to have an optimal algorithm to reveal the charge of your system by only having knowledge of the measurements, you would basically come up with that StatMech model that I told you about. And so that's something we're working on at the moment. So one of the tools that we like to use, that is I like to use, and I guess I'm not the only one, are like those mapping onto StatMech models. There are many reasons for this, that having a classical StatMech model, it's nice. You can simulate them more efficiently. And in the case of the sharpening transition, really, we were able to use relatively standard tools of just field theory, effective field theory that you would, there's some emergent low energy physics, basically because it's non-unitary, right? And of course, there are many open questions, thinking, of course, of higher dimensions, practical ways to observe this in experiments without post-selection. There are many papers working. There was actually one paper yesterday about this. It's a decoding problem in the quantum information language using neural networks. So, there are many, there's a lot of activity to do this more practically and have better ways to probe those transitions in experiments. And there are many interesting connections to decoding problem and quantum error corrections that I didn't talk about. And also in the context of a sharpening transition, we think there is an interesting quantum information perspective to be investigated. And yeah, with this, I thank you very much for your attention. And if you have any question, I'll be happy to answer them.